bigger than J and D. Okay, then of course, as we mentioned, once you sense the difference, you get to a new adaptation point. Then you can actually repeat the process for the second JND. You set this I as the I0 and start the process again. Actually, you can get second JND, third JND, and so on. JND can be the ruler or the yardstick for the measurement. Actually, this is the reason we say we can turn a nonlinear measurement into a linear one. Okay, give you the JND might not need to be IT related and also high tech. So high tech, it can be real everyday life. This is an example. I just searched the internet and then put it here. Someone test the JND for bike in terms of load variation and vibration. Firstly, they record the vibration from the load condition, and then they construct a simulation in the lab. Maybe they construct 10% of the vibration recorded and 20%, etc., up to 100%. And then they use human to test which level of vibration in the simulation the human start to sense the change. So this is the way to measure JND. Of course, you can measure many JNDs if you like. And then, if any other condition unchanged, of course, you like to choose a bike which the biggest JND because it's the most comfortable bike for you. Okay. Okay. Then I come to the more computer and engineering part. Typically, a computational model of JND, like many other engineering models in computer science, is a two-step process. One is the vector or feature extraction. In this context, we use the physical findings and some brain theory and also signal processing technique. And then the step 2 is the Masonality reduction process. Right? We collect all the information and then we produce one single number to tell what is the JND value. Okay, then I give a detailed case study for video and image. There are two reasons for this. One is this is my research area. The other more important reason was actually among all the signals, I believe JND, the JND for image and video are the best investigated case so far. So I use this as example to show you how computationally we can determine the JND for practical use. Okay, so we can model the eye's brain functioning in certain extent. For example, we know the eye and brain have certain frequency response called contrast sensitivity, CSF. It can be spatial, temporal, and combined. Okay, then of course this is a single signal component because we test the sensitivity with the frequency. So, and then we can adapt to the background and setting environment. This is a kind of adaptation, a background adaptation method. Masking is the effect of two or more signals coming together. What happens? The masking is like in the sound, the easier case is for sound. If I'm the only person talking in this room, the voice can be heard best. If two persons talking at the same time, actually, I probably have to raise my voice to be heard. So this is the masking. One signal masks the other signals. And also, this masking effect related to frequency, orientation, etc. structure. Because if two voices are similar in frequency, of course, the masking effect is the maximum. One masks another. Okay, then we can do visual attention model because this take care of the global and local relations. Right. Okay, we talk about this more details. Okay, in operating domain, we can do it in subband, we can do it in pixel domain, we can do the of course, why we do it this way? Because some application is more convenient, use pixel domain. Some application is more convenient to use the subband domain. Of course, there are relations between these two domains, J&D, because they belong to the same process and same mechanism. Okay, then how can we formulate J&D in DCT domain? For example, I choose DCT because DCT is the most popular transform in the signal processing. All the image and video are use DCT hybrid or image coding method. So they are all more or less in DCT domain. So in literature, the sensitivity, the J&D in DCT domain are formulated as a multiplication of different factors. Okay, then firstly, the base factor is due to the special CSF, the frequency response. And then all the other factors are multiplied to elevate the J&D in certain sense. But of course, there is no convincing proof that all the factors to be multiplied together. I do not have this proof. No one does this in the literature also. And this fact actually can be a good attack for reviewers. If you propose something, then people may say, okay, reviewer, the easiest question for the reviewer is, what is the ground? Why not add them together or multiply or combine them together in another way? Okay, this is an unsolved problem. Okay, modeling special CSF, we already have the experiment results from the psychology of the vision study and also the perception science. So we just use those results. We use a formula to fit the experiment result. So nothing, right? It's nothing too much. We just use the result in other field. For the special CSF, we should do something because when the object moves along over the time, actually because you know all the images are projected on our retina, right? So when object moves, the retina image moves. But if we directly calculate like this, we have very big error for formulate our CSF result because our human eye actually have the capability to track the object when it moves. So we have to compensate the eye movement because if the eye follow exactly the 100% the object move, the retina speed of the object is 0. So actually you cannot 100% track the object in the retina. So you actually need to do some compensation in this. A simple compensation is you have the object movement speed projected in the retina. This can be calculated somehow from the existing technology like block matching and also optical flow. After that, you need to somehow compensate the eye movement speed. Okay, so we do this, but I will not go into details because I try to leave all the mathematics. I just talk about the idea due to the time constraint. After model all the factors above, we still have problems because in the perception science, CSF is measured with single frequency, but in the real world image, we have so many frequencies happen at the same time. So how to integrate them together? This is a problem. We do not have the exact clue from the psychology or physiology study, right? So this is a problem. Different authors use different technique to tackle this problem, but the problem is not solved completely. Arbitrary orientation, because CSF is measured with either horizontal and vertical direction only. It cannot be arbitrary in the experiment result. So you have to somehow bridge them to arbitrary orientation. And also, the original CSF is done with the luminance, the real luminance. Now, in that unit, but now we are grade levels. Grade level is not equal 100% to the luminance originally. So we need to take care of this problem. There is no best way so far, right? So I try to tell, according to my understanding, what are the problems unsolved so far. Luminance adaptation is relatively easy because we already know there's the masking effect for the luminance background is something like that. This is background in one area, and this is the threshold in the middle, and the JND is the smallest, and here maybe the bigger. So contrast masking, there are two parts of contrast masking. Intra-band contrast masking is masking by the component's strength itself. That means the higher strength of the signal is, the tolerance for change without being noticed is bigger. So this is the simple formulation. The intra-band, that means other frequency components may be okay. Can be done in the if more frequency masking there, actually the visibility drop as well. Okay, this is just some engineering solution to the masking. The more activity in the block, the masking effect is better, is higher. Okay, then JNT for pixel domain. We can do the luminance adaptation and contrast masking, and you do the JNT. In the formula in the literature, actually for pixel domain they use addition to do. So there's no explanation why in subband domain you use multiplication, and while in pixel domain you use addition. These are the problems. Of course, you can argue if you take a lot of the multiplication, then it becomes addition. This is okay. Some explanation. Okay, this is some of the scheme in the literature. You can actually distinguish the text age structure, right, and then do the evaluation differently for different features. Even you can explore some brain theory like free energy principle. What frequency free energy principle tell us is when the human eye and brain look at a picture, our mechanism in the brain try to predict as much as possible the shape of the structure should be. This is to reduce the surprise. Then, according to this, we separate the picture into orderly portion, which can be predicted well, or is the disordered portion when it cannot be predicted well. For if some errors in this region, our brain can immediately tell the difference. So it's more sensitive in this. While disorder is a random signal, so even you can tolerate more distortion. Right? This is some parts of the pattern masking. This is a regular pattern. This is a random pattern. So we can do a pattern masking, part of the contrast masking we talked about, and also the structure uncertainty, which we use the disorder portion Then this is just some of the mathematical details. We use AR model to predict the disorder portion. We use the local binary pattern in computer vision recognition, pattern recognition. And then we do the Shannon entropy calculation to find out what are the entropy of the distorted portion. That is the uncertainty for the, due to the time constraint, I'm not going to, because I received the signal already on the chat. Okay, so we can do the color difference. This is one paper in the CSVT 10. They do a simple JNT model for color. Of course, they assume this LAB color space is equal distance space for color. So they just set the surface is the uniform one. So we can see a lot of work need to be done. And temporal masking as well. Temporal masking simply is done long time ago, but no progress in the recent years because the masking is so simple. It's just if you have the interframe difference is 0, you get the best sensitivity. If it's not 0, then the greater the difference, the interframe difference is, and then the masking effect is high. But they even did not explain why this is higher than this. So it's very rough ideas so far. Okay, then the last engineering model is the visual attention model. Visual attention is natural mechanism in our human eye. We can spot the most interesting phenomenon in the picture immediately after so many years of evolution in mankind, right? Because our forefather had to spot the lunch quickly and avoid to be the lunch of others quickly. So they do not have the time to scan and process the whole picture and then before they make the decision. So this is the selectivity we already have in our eye. So this have physiological support because in the retina there is a center point called fovea. Behind the fovea there are maximum numbers of sensors. So only the image portion projected on this area, central area, would be maximally sampled and sent to the brain for processing, right? So we can, of course, there are two types of visual attention model. One is bottom up, which is we use the image only, information only. The top down is we use the task of prior knowledge. Because if you are asked to do some task, identify a car, then you may not pay attention to the buildings in the street. Okay, so this is some consideration. This is just an example how can we detect the visual attention out of image or video, right? You detect different cues which attract the attention of human, and then you came up with a possibility of attentional object. The brighter indicates the more attentional area. Okay, then we can modulate the JNT we derived before with this visual attention model because this visual attention model takes care of the local versus the global effect of all the features. Okay, then the current status of JNT development, we found actually there are some answers, but particularly in the image and video. Applications, you can see quality evaluation, coding transmission enhancement, watermarking, and also some computer graphic cases. Okay, if anyone interested in this, you can send me an email. I send you all the reference to you. Okay, but there are more questions than answers in this area. Actually, there are limited of no work in graphic, and there are limited work in graphic animation compared to image and video, and scene and the screen contents, because this is a new area, so understandably not much work here. Audio, speech, there are some work, but not much. These three kinds of signal, basically very limited work. Enhancement is not done properly. Multimodality research is lacking. And also, utility based on JNT and personalization JNT is basically not done. Okay, then I maybe quickly go to, we complete the major part of this talk already. I just maybe share with you what kinds of future work may be interesting to us. Okay, of course, the first point is those pointed out in the previous slide obviously need more investigation because they are not done sufficiently. Okay, then I think computer graphic and animation need more attention because actually, you know, all the contents creating company maybe spend a lot of time, like the movie companies spend a lot of time and maybe a few weeks for high quality graphic contents creation. Actually, we can reduce that effort, use the JNT model. Because if something, the difference is below JNT, why spend so much time in just try to figure out what is going on? This is some initial result. Actually, you reduce the effort, it is hardly noticeable. Okay, then another point I think computer graphic is important or meaningful is actually in image processing, we spend a lot of effort to try to get high level information like the object segmentation, the object movement, also what is inside the image without much success. But in computer graphic, this information, high level information is available to us because we have all the models. So in this case, I hope actually JNT estimation would be somehow easier or more meaningful or less error prone. Okay, then we can include the more semantic the information into JNT model. For example, I know a few companies already built up some local brands recognition systems. Then if we can build some semantic information to it, then we can actually to detect whether the changes is too much or too small or